We'll continue where we stopped last week. So last week we started looking at another kind of search algorithms, which are typical in nature, which are referred to as hill climbing search or hill climbing algorithm. And as it reads over here, hill climbing algorithm, if you go through these steps, you will feel like you are climbing a peak in thick fog with amnesia as a characteristic. That is, you do not remember how you reached a particular point. Besides that, you reach that point. So you're very much looking at neighborhood which is very short in nature. You don't know from where you came up to this point, and you also don't know where exactly you're headed towards. So that's the situation where hill climbing algorithms would be a solution technique preferable. That is, I have a very large, huge state space, and I don't know exactly. Uh, I can't actually have the capability, maybe, to remember all the paths that I navigated so far or that I will be navigating maybe in future. So that is where these algorithms will come in handy. The other place where such algorithms come in handy is when I'm interested in reaching the goal and I'm not interested in knowing this solution sequence. So far, when we define the AI problem, which is input to this function as well, what we were interested in was the action sequence that will lead me from initial state to the goal state. So somewhere the solution was a sequence of actions, okay? But there are certain problems which can also be termed as AI problems, or which can also be defined as problems, state space problems, okay? And such problems, we might not require the action sequence, but we are more interested in reaching the goal node. The problems that you can think of which can be categorized into this category could be all the problems where you want to schedule certain things, like maybe layout of a VLSI circuit on a given map of wafer. So I have a wafer, silicon wafer given to me, and on that, or whatever material wafer that it is given to me. I'm not an electronics engineer, so I'm not sure whether it is silicon wafer or whether it is wafer from some other material. But I may have a certain material wafer available to me in some size, maybe some width and some breadth. What I know is I want to place so and so many number of electronic components. There may be some sort of circuits, there may be some sort of chips, there may be some sort of, say, gates or whatnot. Okay, and I just know the component count, that this particular size material needs to house these many components, such that I should be able to produce this output. So this configuration is what we want to do. We don't require in this case to actually do multiple actions, impart them on the environment, get the result, understand the change in the environment, put the next action to the environment. Such interactive behavior is not meant for, or is not required in such problems. The other problems that I can think of would be any institute or any college. When we set up our schedule or timetable, there are certain constraints that we need to follow for that timetable. Plus, that timetable should cover or should be used for a certain amount of time. So all these scheduling problems, which may involve timetable scheduling, which may involve scheduling of flights for a particular journey from one place to the other place, so on and so forth, you would definitely be uh, tempted to use an algorithm that is like a hill climbing algorithm. Okay, so that's the basis for why I should go for hill climbing algorithm, or why should I do hill climbing search. Because hill climbing search is not searching for the solution sequence or action sequence, it is searching for the goal configuration. So all the problems that come in the category where we want to configure the environment state into a particular one as my goal, then such problems are tick for using hill climbing search. The drawback of hill climbing on now is that this algorithm doesn't guarantee you an optimal solution. So you won't be getting an optimal solution. So you may have for a problem, say 20, 25 or 30 number of say constraints that the goal state must satisfy in order to say that I have reached the goal node. Whereas a hill climbing like algorithm might give you a solution, or it might say that you have reached a solution of the problem when it actually has certain state where there are only 29 or 28 or 27 or some less number of constraints are satisfied and some constraints are still violated. Such solutions we will be referring to generally as a local maxima or local minima. So this problem in a way it is presented to you is a hill climbing or optimization problem where we want to maximize the objective function because we are viewing it as an objective function. But this can well be defined as a reverse problem as well, where I want to minimize the cost to a least value. And that is how we know these algorithms when it comes to machine learning, when it comes to deep learning or neural networks. There, what we want is the classification error must be minimized by the model that we want to fit our data to. So in machine learning, we generally view this particular kind of algorithms as a downhill problem. So whether you consider it as a downhill as it discussed in machine learning case, where our optimization objective is to minimize certain functions value. In this case, we are using an objective function as a maximization objective. So that is how these problems can be seen as dual of each other. So the algorithm that we are representing over here is hill climbing, but please understand this can also be turned upside down, and I can define it to be climbing down a hill or downhill problem. I can represent this as a downhill problem as well. There would be slightest of the change. Here I was trying to increase the benefit. There I will be trying to decrease the benefit because decrease the cost that will be incurred in a particular step. Okay, so that I guess summarizes what we already have seen last week. I'm again looking at this particular problem because there is a lot of discussion that is going to come ahead, which is going to be dependent on this particular algorithm called as hill climbing algorithm, right? So the algorithm is in front of you. You are looking at it. So the name of the algorithm is hill climbing. Problem is the input and output is local maximum. We already said that this is what this algorithm is going to give you. So we are not expecting a global maximum. So global maximum will be the maximum value that the objective function can reach for the entire domain the objective function input has. Okay, so that is global maximum. Local maximum can be various things for various localities in the whole graph of or whole range of inputs that the objective function can have. Okay, so please understand that local maximum does not have any limit such. Anything can be a local maximum. A very negative value can also be a local maximum. A very much large value can still be a local maximum. Or a zero can also be a local maximum in a locality of reference. That is what local maximum means. Now, the inputs to this particular algorithm is the well-defined state space problem. We already know what it is. So we need not discuss it. The local variable that you will be using are two node data structures. The problem actually defines a node data structure as well. So that node data structure, two instances or two objects are my local variable. One object is referred to as current and the other object is referred to as neighbor. So two node objects are created and I have a problem which is defined. These three variables are sufficient for me for this algorithm to run. What we do is we start with the initial state of the problem. So we access what is the initial state of the problem and we spawn a node out of it. That is, we define a node for initial state. So we define all those 5 things which are required to define the node, okay, from the initial state of the given problem, that we assign to the variable, local variable called as current. So this is the current node that I am looking at. What next I will be doing is I will be into going inside a infinite loop, that will do what? That will every time expand the current node, check the successors for the highest valued objective function, okay, amongst the successor of current node, that will be assigned a name called as neighbor. So this is the target, or the this node, the neighbor node, is one of the child nodes of the current node that can replace the current node as a next step in the algorithm. Okay, so what we are going to do now is we are going to consider neighbor node to be current node only when the value of neighbor, okay, is greater than the value of current. So value is of what? Value of the objective function. So this value square bracket neighbor means we are accessing the objective function value given the state of the neighbor node. Okay, so value of current means we are accessing the value of objective function given the state of the current node. So current is a node data structure. We are accessing the objective function value when we are accessing the value, and we are comparing it with each other. So if current node's objective function value is greater than neighbor node's objective function value, then what it indicates? It indicates that the current node is having better objective function value than the best neighbor of the current node, or best child of the current node. So current node is much better solution. We better off stay here and we need not go to the next step. That is how we are returning the current state as the local maxima. That is what we are doing in step number 2. Step number 3 will happen whenever this condition is false. That is, the neighborhood node has objective function value better than the current node. So there is at least one node better, having better value than the current node. So I must say I should concede my place as current node to the neighbor node, and that is exactly we are doing in the third step in the algorithm. So algorithm, very sleek, very small, and very intuitive. We are just checking against all our successors whether one, the best of the successor, is having better objective function value than me. If it is so, I concede my spot to him. If not, I will be the winner in this case, and I will be getting myself returned as a local maximum. That's the explanation of the algorithm in one single statement. Okay, I hope this algorithm is